Welcome back, everybody. So let's continue with our proof of completeness, trying to build out a model out of a set of sentences. So remember we had our set of closed terms. These are the terms that have no variables, and we are using the bracket T to denote the equivalence class of the term T. T is a term, a string of symbols, nothing else. But we have this equivalence where two things are equivalent if you can prove that they are equivalent, formally prove that they are equivalent. Okay, so now let's go to the general case and build this model. So suppose now our vocabulary is like a standard thing, contains some constant symbols, some function symbols, and some relation symbols. And okay, I'm repeating here the same thing. T is equivalent class of T. So let's consider this now as a tau structure. We want a tau structure. So let me just write it down. That means that it has a domain and it has an interpretation for all the symbols in tau. So okay, the domain, we're going to use this quotient that we defined in the previous video, which is a set of all closed terms, modulo the equivalence relation that tells you that two terms are equivalent if gamma can prove that they are equal. Okay, when gamma can prove they are equal, we make them equal in this quotient. Okay, so that's our domain. It's a set of terms under that equivalence. And then we need to interpret the constants. We call this gamma, this C sub 0 super gamma, to be the interpretation of C0, and the same for the functions and the same for the relations. Let's see what those are. The interpretation of Ci is going to be the equivalence class of Ci. Ci is a constant symbol. So if you just consider it by itself, it's a term, it's a closed term. So the interpretation of Ci is going to be the equivalence class of that term. That makes sense. So everything that you can prove, the set of all things that you can prove is equivalent to Ci. What about the functions? The functions is a bit tricky, because now this is a functions, the function that we want to define. So fi here, f1 is a function symbol. And how is that we define an interpretation of a function? Well, we have to see what it does as a function. How does it work as a function? So the input of a function is going to be, if you have a k array function, in this case, this function is taking k inputs, we assume. So what are the inputs? Well, the inputs are things from this quotient, right? So that means they are equivalence classes of terms. So that's what I wrote up here. Equivalence class of a term, equivalence class of a term. So you have a k equivalent class of terms that you input to this function, and you're supposed to get an equivalent class of a term, right? So let me write that down. F gamma is a function that goes from the set of k tuples of equivalence classes to a single equivalence class. When we define a function like that, we always have to be careful that we're doing, that the function is well defined. What does it mean well defined in this case? Well, here we're inputting a whole equivalence class, and here another equivalence class, but suppose we take a different equivalence class. So suppose that we have S1 is a term that is equivalent to T1, and S2 all the way up to Sk is a term that is equivalent to Tk, right? Then we have that the equivalence class of Si is equal to the equivalence class of Ti. So that means that if we if you look at S gamma F1 applied to the equivalence class of S1 Sk, we should get the same thing, right? Because this guy is the same as this one is the same as this one, so this should be the same as that. So the result, what we're getting here, is the equivalence class of this guy. So for those to be equal, what we claim here that needs to happen is that this guy is irrelated to F gamma T1 Tk. Okay, so that's enough to say that the definition makes sense. this requires a proof, right? So this requires a proof. And the proof is going to follow from something we mentioned last week, which was that equality is a congruence relation. And that didn't just imply that it's an equivalence relation, but also that it behaves well according to with respect to the relations and the functions. So here is the important one that we need now, and is that if you have a function, in this case we were using a binary function just for the example, but it doesn't really matter. If you have that x, you can prove this line, you can prove this sentence out of nothing, just from the logical axioms without any assumption, that for every x, y, x prime, y prime, if x equals x prime and y equals y prime, then f applied to xy is equal to y applied to y prime, right? So we said you can prove this. This requires a proof. I recommend you guys try it. A deduction, a formal deduction. You can do a formal deduction of this. So you can show here from gamma, well, from nothing actually, that if S1 equals T1 and Sk equals Tk, then f of S1 Sk equals f T1 Tk. So this is something that you can prove out of nothing, right? So that means, having this is just an instantiation of what we had before of this thing up here. It's just an instantiation of this. And we know because of this that you can show that gamma shows S1 equals T1, gamma shows that Sk equals Tk. So putting all of these together and using essentially just the fact that these guys together with this one, they tautologically imply what? They tautologically imply that gamma shows that f of S1 Sk equals f of T1 Tk. And once you have that, that's going to give you the equivalent. So once you get this, then you get that these functions, these strings of symbols are related according to E. And that's why you get a congruence relation, and that's why this definition is correct, it's well defined. Okay, so that means that's how you define the function symbols in this quotient. And how do you define the relations? Well, you do something similar. I remember a relation. Let's go to a new clean page. The interpretation of a relation of additive k, in this case we have additive k, is going to be a subset of this quotient m gamma. This is the quotient. That's m gamma to the k. So it's a set of k tuples from k. The set of all the things that essentially satisfy the relations, right? That's the interpretation. The set of all things that satisfy the relation. So those are these interpretations that we have up here. They are a subset of this set of tuples. And the definition here is that this tuple is going to belong to the interpretation if and only if you can prove that the relation is true on them. Okay? Again, you need to show that this is well defined, because here we have the same story. What we can show now is that if we have that S1 is equivalent to T1, so on and so forth, Sk is equivalent to Tk, then gamma proves that R0 holds of S1 up to Sk if and only if gamma proves that R0 holds of T1 up to Tk, because they are equal. So this again requires a proof, and the proof again follows from the congruence of equality that we had last week, and using that part up here, that if you had a relation symbol, in that case we did binary just to simplify the notation, and you can prove that x equals, well, if you know that x equals x prime and y equals y prime, then Rxy holds if and only if R of x prime y prime holds. So these, together with our assumptions, are gonna tell you that this is the case. You need to build a deduction. I let you guys try it, but then you're gonna get that this is well defined. It doesn't matter. So if you take an equivalence class here, doesn't matter which representative you take, whether you take T1 or S1, you're gonna still get the same definition. Okay, so that finishes the definition of the structure. So the structure has interpretation for constant symbols and relations, and those are the definition. So that's the definition from a structure out of gamma. The next step is to figure out whether this is going to satisfy gamma. Notice that in the examples that we saw before in the last video, essentially we were considering this structure already, more or less. That was kind of in the back of our minds. So this is the same intuition we had when we did the group and this other group and the field, that we have these elements with terms, and essentially we think of them as multiply. We can think of how we can multiply and add these terms. Essentially, that's what we're doing. So the question now is, what if this structure is a model of gamma or not? The answer is going to be, it's not that simple. See you guys later.